Okay, welcome to another video on the Python for DevOps book. This is virtualization and containers. There is no more fundamental component of the cloud than virtualization. When AWS officially launched in 2006, Amazon Elastic Compute Cloud EC2 was one of the core services released. There are a few key areas of virtualization to discuss. Hardware virtualization. The first virtualization abstraction released by AWS was hardware virtualization. Hardware virtualization comes in two flavors: paravirtual, PV, or hardware virtual machine, HVM. The best performance comes from hardware virtual machine, or HVM. The critical difference in performance is that HVM can take advantage of hardware extensions that tap into the host's hardware, essentially making the virtual machine a first-class member of the host's hardware, rather than merely a guest that is unaware of what the host is doing. Hardware virtualization provides the ability to run multiple operating systems on one host and the ability to partition CPU, I/O, both network and disk, and memory to the guest operating system. There are many advantages to this approach, and it is the foundation of the modern cloud. But there are also some unique challenges to Python itself. One issue is that often the layer of granularity is too large for Python to fully exploit the environment. Because of the limitations of Python and threads, they don't work on multiple cores. A virtual machine that has two cores could be wasting one core. With hardware virtualization and the Python language, there can be a tremendous waste of resources due to a lack of true multi-threading. A virtual machine configuration for a Python application can often leave one or more cores idle, wasting both money and energy. Fortunately, the cloud has presented new solutions that help eliminate these defects in the Python language. In particular, containers and serverless eliminate this problem because they treat the cloud as an operating system, and instead of threads, there are lambdas or containers. Instead of threads that listen on queues, lambdas respond to events from a cloud queue, such as SQS. Software-defined networks. Software-defined networks, SDNs, are an essential component of cloud computing. The killer feature of SDNs, or software-defined networks, is the ability to dynamically and programmatically change network behavior. Before this capability, this often rested in the hands of a networking guru who managed this F5 load balancer with an iron fist. Noah once worked at a large telecommunications company where there was a daily meeting called change management with a single individual, let's call him Bob, who controlled every piece of software that was released. It takes a unique personality to be a Bob. There were often yelling matches between Bob and people in the company. It was the classic IT operations versus development battle, and Bob delighted in saying no. The cloud and DevOps completely eliminate this role and the hardware and the weekly shouting matches. Continuous delivery processes are building and deploying software consistently with the exact configuration, software, and data needed for a production environment. Bob's role melted into ones and zeros deep inside the matrix, replaced by some Terraform code. Software-defined storage. Software-defined storage, SDS, is an abstraction that allows storage to provision on demand. This storage can be configured with granular disk I/O and network I/O. A good example is Amazon EBS volumes, where you can configure provisioned disk I/O. Typically, Cloud SDS grows disk I/O automatically with the volume size. An excellent example of how that works in practice is Amazon Elastic File System, EFS. EFS increases disk I/O as the storage size grows. This occurs automatically and is designed to support requests from thousands of EC2 instances concurrently. It also has deep integration with Amazon EC2 instances that allow pending writes to buffer and occur asynchronously. Noah has good experience using EFS, Elastic File System, in precisely this situation. Before Amazon Web Services, AWS Batch, was available, he architected and wrote a system that employed thousands of Spot instances that mounted Elastic File System, EFS volumes, where they performed distributed computer vision jobs they collected from Amazon SQS. The ability to use a distributed file system that is always on is a massive advantage for distributed computing, and it simplifies everything from deployment to cluster computing. Containers. Containers have been around for decades, and they refer to OS-level virtualization. The kernel allows the existence of isolated user space instances. In the early 2000s, there was an explosion of hosting companies that used virtual hosting of Apache websites as a form of OS-level virtualization. Mainframes and classic Unix operating systems such as AIX, HP-UX, and Solaris have also had sophisticated forms of containers for years. As a developer, Noah worked with Solaris LDOM technology when it came out in 2007, and was in awe at how he could install full operating systems that allowed granular control of CPU, memory, and I/O, all from telnetting into a machine with a lights-out management card. The modern version of containers is under rapid development, borrows the best things from the mainframe era, and combines them with newer ideas like source control. In particular, one of the significant revolutions with containers is to treat them as projects that check out of version control. Docker containers are now the standard format for containers, and all major cloud vendors support Docker file containers, along with Kubernetes container management software. There is more information on containers in Chapter 12, but the essential items that relate to the cloud are listed here. Container registry. All cloud providers have a container registry where they keep your containers. Kubernetes management service. All cloud providers have a Kubernetes offering, and this is now the standard for managing container-based deployments. Docker file format. This is the standard for building containers, and it is a simple file format. It is a best practice to use lint tools like Hadulint in your build process to ensure simple bugs don't leak through. Continuous integration with containers. All cloud providers have cloud-based build systems that allow integration with containers. Google has Cloud Build, Amazon has AWS Code Pipeline, and Azure has Azure Pipelines. They all can build containers and register them into a container registry, as well as build projects using containers. Deep container integration into all cloud services. When you get into managed services in platforms on clouds, you can rest assured that they all have one thing in common: containers. Amazon SageMaker, a managed machine learning platform, uses containers. The cloud development environment, Google Cloud Shell, uses containers to allow you to customize your development environment. Okay, I'll be back shortly. All right, challenges and opportunities in distributed computing. One of the most challenging areas of computer science is distributed computing. In the modern era of cloud computing, there are a few fundamental shifts that have changed everything. One of the most significant shifts is the rise of multi-core machines and the end of Moore's Law. So it looks like Moore's Law ended in about 2014, and Moore's Law, from what I understand, is every 2 years the power of computers is going to double and the cost of computers is going to be to half. So here we've got the performance of a computer as compared to this benchmark here, and then we've got the year here. So we can see every year the performance is increasing, and we can see from the 80s all the way up to 2003, 2004, we've got tremendous rapid growth of this. But now as we're starting to get to the present time, we can see this is kind of leveling off, and now this is actually not increasing the same way anymore. And this kind of makes sense intuitively. I mean, imagine, for me, I was a child around this time. This is when I finished my 2004 would have been when I finished high school. So I saw this every year. I saw computers drastically change, and when I was a kid, I saw the big floppy disks, the A drive, and then when I graduated from high school, things were much different. And now, of course, I'm playing VR quite often, so there's still a lot of improvements happening. But one thing that I am noticing is I can now buy a computer that's a few years old, and I'll get roughly the same deal as if I were to buy one that is brand new. So that was not at all the case in this area. The moment you bought a computer that was a few years old, you bought a computer that was basically useless. It was so far out of date. Moore's Law exposed two fundamental problems that manifest themselves in the cloud era. The first problem is that CPUs are designed to be multi-purpose processors. They are not specialized to run parallel workloads. If you couple that with the ultimate physical limits of increasing CPU speed, the CPU has become less critical in the cloud era. In 2015, Moore's Law was effectively over, and gains are at 3% a year. Oh, okay. The second problem is that making multiple core machines to counteract the limitations of single processor speed has led to a ripple effect on software languages. Many languages previously had substantial problems taking advantage of multiple cores because they were designed in an era before multiple processors existed, let alone the internet. Python is a good case in point here. What makes things even more challenging, figure 9.8, shows that there is no free lunch by adding more cores to a problem that is not mostly parallel. Okay, so we can see here we've got the portion. So we've got, this is Amdahl's law. So we've got how much of a speed up you're going to get, and this is the number of processors you add. So when you're working on something and you've got one processor, you're going to have that function at here, which looks like it's functioning at a unit of 1. So if you add another processor, it looks like okay, so let's say you add another processor. So if you're using only 50% of each processor in parallel, you don't get much of a performance increase. But if you're using 95% of each processor in parallel, you get a much more bigger increase. And as you add more and more processors, um, the higher the amount of parallel processing you can do, the more of a speed up you can get. But you can see for all of these, there's a limitation to how much speed up you can get, and just adding more and more and more processors to the problem only gets you to a certain point. If you want to go beyond that point, you can't just simply add more processors. The opportunity is in the cloud and different architectures like application-specific integrated circuits, ASICs. These include graphic processing units, GPUs, and field programmable gate arrays, FPGAs, and tensor processing units, TPUs. These specialized chips are increasingly being used in machine learning workloads and are paving the way for cloud architectures that use a combination of different hardware to tackle complex problems in distributed computing. Python concurrency, performance, and process management in the cloud era. Imagine walking down a dark street in San Francisco late at night in a dangerous part of the city. In this scenario, you are a black belt in Brazilian Jiu-Jitsu. Oh my God. You are alone and notice a stranger seems to be following you. Your heart starts to race as they approach, and you think about your years of martial arts training. Will you have to fight a stranger in the street? I mean, I'm not sure if that's what you'd be thinking if you were trained in martial arts. You effectively spar with opponents at your gym several times per week. Yeah, I really think if you were like, because I think they train you like avoidance and situational awareness. So like, first of all, they probably wouldn't recommend that you be in San Francisco in a dangerous part of town late at night if you can help it. And then if you can't help it, they would probably recommend, if the stranger is following you, to think about how can I not fight this stranger instead of what if I have to fight the stranger. You feel prepared to defend yourself if you need to. You also know that Brazilian Jiu-Jitsu is an efficient martial art, and it works in real-world situations. On the other hand, fighting someone is still something to avoid. It is dangerous, weapons could be involved, you could win the fight, yet seriously injure your opponent. You could lose the fight and become seriously injured yourself. Even an expert in Brazilian Jiu-Jitsu knows that a street fight is not a preferred scenario, despite the high probability of winning. Concurrency in Python is very similar. There are some handy patterns like multiprocessing and async I/O. It is better to use concurrency sparingly. Often the other option is to use the platform's concurrency options, serverless batch processing spot instances, versus the concurrency you create yourself via a programming language. Process management. Process management in Python is a standout capability of the language. When Python acts as a glue to other platforms, languages, and processes, this is when it is at its best. Also, the actual implementation of process management has dramatically changed over the years and continues to improve. Manage processes with subprocess. The simplest and most effective way to launch processes with the standard library is to use the run function. As long as you have Python 3.7 or higher installed, start here and simplify your code. A hello world example is just a line of code. Oh, that's interesting. So this is run. I usually do check output, but let's highlight this. This line does almost everything you might want. It invokes a shell command in a Python subprocess and captures the output. The return value is an object of type completed process. This has the args to launch the process. The return code, std out, std error, and check_return code. This one-liner replaces and streamlines overly verbose and complicated methods of invoking shell commands. This is great for a developer who frequently writes Python code mixed with shell commands. Here are a few more tips that might be helpful to follow. Avoid shell equals true. It is a security best practice to invoke a command as items in a list. It is best to avoid using a string. Avoid this. Subprocess.run ls-la shell equals true. The reason for this is straightforward. It is easy to introduce a security hole accidentally if you accept any string and execute it. Let's suppose you write a simple program that allowed a user to list a directory. A user can backdoor any program they want and hitchhike on your program. Writing an accidental backdoor is very scary and hopefully illustrates what a bad idea it is to use shell equal true. So this is input by a malicious user and causes permanent data loss. User input equals some. Yeah, I don't get it, because for me, like when I use, because like I prefer this, it's just a lot easier because it's just the actual command you put in there. But what I don't do is this. Like it seems like what they don't want you to do is allow the user to provide input here. And from what I understand, this doesn't do that. Like, yeah, now this always gets me, because it seems like what you see a lot is people just freaking out saying, oh, don't do it like that, don't do it like that. But they don't understand why not to do it like that. And here it's you know, it's made very clear you don't do it like that because you're allowing a user to run any commands. But the thing is, you can write it this way too, and you can say here, you can give a variable here. So if the user, so you can, here you've got user input. So I don't get it. Personally, I probably wouldn't continue to use shell equals true if I could figure it out this way, but if you're new to Python, you're trying to get things to work, you want it to go vroom, just use shell equals true and don't use a variable here, and don't allow the user to provide input here. Like a lot of the times when I need to use this command, I don't have a variable here. Like it'll look like this more often than it will look like this, and this doesn't allow a user to enter just whatever they want, because the problem is that this user input variable is plugged in here. You can see my command equals ls-al plus user input. So this is what is problematic, not shell equals true. That's not problematic. So this would be just as much of a problem if you used this sort of syntax, passing in a list, as it is passing in this shell equals true. Because yeah, like the user input, if they say some dir and like that here, yeah, that's not going to work. But they can okay, well, I guess it is a little bit more secure, but yeah, because if you were just, if you were to write it like this and then you just have them here, then they could just put whatever they wanted in there. But here, it's going to be a little bit harder for them to do that. Instead, you can completely prevent that by not allowing strings. This is input by a malicious user and does nothing. So you can see here, You're allowing just a complete string to be added here, so they can add they can say change to some directory and then remove the whole directory. But if you put it this way, this is input by administrative user and does nothing. Now when they enter that, it goes in as a yeah, I don't know, like, because I think you can still. I'm actually kind of curious. I'm gonna do an experiment here. So I lost my place in the book, but I've got a bookmark. Okay, so let's do an experiment with IPython. Okay, so I've got IPython here. So let's try these two methods here. We're gonna first try the one that they don't recommend. So we'll do exactly as they have it listed. We're gonna say user input equals, and let's do this. So we're gonna quit out of here. We're gonna do a ls, or sorry, a dir, and then we'll say we'll say touch do not delete .txt. Oh, let's do a notepad, because this is not Linux, this is Windows, so we'll do notepad. Okay, we'll make a new file called, and we'll say don't delete me. And then we'll go and then we'll create a new file. Oh, I did cd, not code. I thought I did this command. Okay, so now let's make two new files here. The first file, we're going to call it rightway.py. And then the second file will be wrongway.py. Okay, so the right way to do it, according to the book, so we've got user input, so let's do the command, let's say user input equals input, say do not abuse. Okay, and then we'll say my command equals ls, and we'll say dir plus user input. Okay, and then we've got to import subprocess. Okay, and then subprocess.run my command shell equals true, and we'll print out the command that is run. Okay, so this is the wrong way to do it. So let's run this file here. It's called wrong way, or sorry, called right way. This is the right way to do it. Okay, so do not abuse. We're not going to listen to that. Oh, actually, this is the wrong way to do it. So I'm gonna move this over here. We're learning about the wrong way to do it. So we're gonna see how this can be abused. So let's try this again. Wrong way. Okay, so do not abuse this. But you know what? They set it up wrong, so we can certainly abuse it. So what we're going to do is we're going to enter ampersand ampersand, and then we're going to say del do not delete .txt. And we see the do not delete file disappears because we were able to enter in extra commands that the script was not expecting us to enter because we did it the wrong way. All right, so naturally, you would think doing it the right way would prevent that, and we wouldn't be able to delete that file anymore. So let's see if that's the case. Okay, so the right way to do it would be user input equals input. It'll be this. So everything will be the same, pretty much. But the difference will be here. When we do the process.run, we're not going to use shell equals true. Instead, we're going to pass a single argument, which is going to be a list, and then each element in the list is going to be the command we want to run. So the first one, we're going to run dir, like we did before, but then the second one, we're going to run the user input. Okay, so we've got the, I'll have a, okay, so now that it's the right way, let's see what happens when we do that exact same thing and we pass it the exact same output that we did before. So we'll pass right way. Okay, so yeah, this is actually this kind of changed my mind a bit because I think these elements in this list apply to the first element. So I can't do something like del now because del is not another flag you can attach onto the ls command. So if I were to do, the dir command. So I could do another. Yeah, I can't even do another, or let me see here. Let me take this out. Cool. So even with this, yeah, we can see this is a much better way to do it. Because instead of just running a whole string of commands, it only allows the user input to be applied to the commands that are the command that begins your list. That is the 0th element of your list. So if remove rm-rf is not a flag for the ls command, it will not run. So much better way to do it. I'm going to be more careful about that going forward. Set timeouts and handle them when appropriate. If you are writing code that invokes a process that may take some time to run, you should create a sensible default timeout. An easy way to experiment with how this works is to use the Unix sleep command. Here is an example of a sleep command that finishes before the timeout triggers in the IPython shell. It returns a completed process object. Okay, so yep, now we've got the completed process object. Here's a second version that throws an exception. In most cases, it would be wise to do something useful with this exception. A reasonable approach is to catch this exception, timeout expired, and then to log the exception and implement some cleanup code. All right, let's follow along with these examples. They look very doable. Okay, so we're going to do sub process.run, and now we're going to use that method of input to this. We're going to use the list argument instead of shell equals true for security purposes, because then when we enter the 0th element of the list here, all other elements of the list are specific to that first element. So sleep has an argument that can be passed to it, which is the length of time in seconds you want the sleep to occur. So that can be added to that list. Anything else added to that list will not execute unless it is allowed by the sleep Linux command. Okay, and then we can add more arguments to our .run method. If it's trying to run a command and the command is hanging, you can make sure that after a specified amount of seconds, it just won't try out again, and it will end. And that's really good to do so that you're not just sitting and waiting for something that's frozen. Okay, so I don't have the sleep command in Windows. All right, so, okay. So, you know what, let me just do the dir command then. Because I'll get back the same object. It's going to be a completed process object. Okay. Why did that not work? That didn't work. Let me try this. See, this is the problem. It's like, okay, this is insecure, but it works. Like, the other way just randomly doesn't freaking work. It's like, what am I to do? Like, I have to get it to work. Like, I'm sure it's more secure doing the other way, but it's probably more secure because it doesn't freaking work. All right, so yeah, I'm not sure what to do about this. Maybe if I get rid of the timeout. Yeah, it's not finding this dir here. So, See, it only works with the shell equals true. But I think that's fine as long as you're not accepting user input here, and that's just all hard-coded. I really don't see the risk. Okay, so this didn't work, but let's try the next example. Oh, so, okay, so the next one is starting here. Oh, so this isn't going to work either because I don't have that. Oh, but I have a try except block now, so it'll trigger the except code. But it'll only trigger it for a sleep command timeout, which the sleep command is not going to execute. So let's just move on. Logging exceptions are critically important when building systems at the professional level. If this code is later deployed on many machines, it could become impossible to track down an error without a centralized logging system that is searchable. For DevOps professionals, it is critically essential to follow this pattern and evangelize its usefulness. So the pattern is a centralized logging system that is searchable. All right, the problem with Python threads. You may have had a friend your parents told you not to hang out with when you were growing up. If so, it was most likely because your parents were trying to help you avoid bad choices. I actually have never had that. Python threads are a lot like that lousy friend you had growing up. Things are not going to end well if you keep associating yourself with them. I guess I'm lucky because I never had like the friends I had growing up were like I never had like lousy friends. I had like when I was really younger I had like bullies and then like friends. So I never had like intermediary like friends, I guess. I don't know. I guess I just got lucky. I had a decent childhood, I think, for sure. Threads in other languages are a reasonable trade-off. In a language like C++, you can execute thread pools that connect to queues and expect that each thread that spawned can take advantage of all the cores on the device. This well-proven pattern of using threads with queues decreases the downsides of manually setting and removing locks in code. Python doesn't work this way. If you spawn threads, it won't use all of the cores on your machine. It can often behave in a non-deterministic fashion, bouncing from core to core and even slowing down your code. Why use something like this when there are alternatives? If you are interested in learning more about DevOps, then chances are you're focused on pragmatism. You only want to learn and apply the knowledge that is practical and makes sense. Absolutely, that is what this channel is all about right now, but that is really hard. Pragmatism is yet another reason to avoid threads in Python. In theory, you could use threads in, oops, and I lost my place. I don't know if I will get it back, because I just took my, oh, I got it. Some situations and get a performance increase if the problem was IO bound. However, again, why use an unreliable tool when reliable tools exist? Using Python threads is like driving a car that requires you to push it and jumpstart it by popping the clutch because the battery is flaky. What happens the day you don't have room to jumpstart it or can't park the car on a hill? Using this strategy is pure madness. There are no examples of using threads in this chapter. Why show something that is incorrect? Instead of using threads, focus on other alternatives outlined in this chapter. Yeah, so I use threads. So it looks like multiprocessing is a better way to go. So yeah, this is a really good book for me to read. Throw out some of my bad habits in coding. Using multiprocessing to solve problems. The multiprocessing library is the only unified way to use all of the cores on a machine using the standard library in Python. In looking at Figure 9, there are a couple of options at the operating system level: multiprocessing and containers. So this is running parallel Python code. We've got the cloud, operating system, multiprocessing container, multiprocessing container, and then cores. Using containers is an alternative, as an alternative is a crucial distinction. If the purpose of using the multiprocessing library is to invoke a process many times without inter-process communication, a strong argument could be made to use a container, virtual machine, or cloud-native construct such as function as a service. A popular and effective cloud-native option is AWS Lambda. Likewise, a container has many advantages for forking processes yourself. There are many advantages to containers. Container definitions are code. Containers can be sized precisely at the level needed. For example, memory, CPU, or disk I/O. They are a direct competitor and often a better replacement for forking processes yourself. In practice, they can also be much easier to fit into a DevOps mindset. From a DevOps perspective, if you buy into the idea that you should avoid concurrency in Python that you implement yourself, unless it is the only option, then even the scenario when you use the multiprocessing module is limited. It may be that multiprocessing is best used as a tool in development and experimentation only, since much better options exist at both the container and cloud level. Another way to put this is to ask who you trust to fork processes: the multiprocessing code you wrote in Python, the developers from Google who wrote Kubernetes, or the developers at Amazon who wrote AWS Lambda. Experience tells me that I make the best decisions when I stand on the shoulders of giants. With that philosophical consideration out of the way, here are some ways to use multiprocessing effectively. And I agree with that, but to be honest, sometimes I find like, some of this stuff might be behind a paywall, some of it might require doing it in a certain way that's confusing. So sometimes just writing it yourself is not the worst way to do it. I mean, as I said, the most important thing I think is to make it go vroom. So if you can do that using a sports car, that's great. But if you just ride your bike, you can get somewhere all the same. As long as you've got enough time to get there, you're there. Forking processes with pool. A straightforward way to test out the ability to fork multiple processes and run a function against them is to calculate k-means clustering with the sklearn machine learning library. A k-means calculation is computed intensively and has a time complexity of O to the n to the second power, which means it grows exponentially slower with more data. This example is a perfect type of operation to parallelize, either at the macro or the micro level. In the following example, the make_blobs method creates a dataset with 100,000 records and 10 features. This process has timing for each km-means algorithm, as well as the total time it takes. Okay, well, you know what? Let's try this. We're going to get sklearn. I've got a Python virtual environment here. So if that takes some time to download, I'm going to take a break while that's downloading. But let's take a look. Okay, it's going to take some time to download, so I'm going to take a break. I'll be right back. Okay, I'm back. I'm recording. I've got sklearn now, so let's see if this is going to work. Okay, so we're trying to import a method from there. So, oops, we didn't get we got a no module named. So let's make sure I spelled everything correct. So we got sklearn, datasets, samples, generator with an underscore. So I spelled everything correctly. Oops, but it looks like I forgot the letter A here. MAKEBLOBS. Oops, misspelled it again. BLOBS. So it looks like MAKEBLOBS. So it looks like this sklearn. So I've got I've got an error there. sklearn. Okay, so I can import sklearn. Let's see if we've got sklearn.datasets. We do. How about .samples? Okay, so we don't have this samples generator here. You know what? Let's try this. We're going to do a update on pip install, and then we're going to try downloading this again. So we'll do pip install update pip, or pip install update pip. Oh, there it is. So it's going to be pip install upgrade pip. Oh, upgrade. Perfect. Okay, now it's working. So now that that's upgraded, let's try installing sklearn again. Might get a more recent version of it. Oops, so we've got could not install packages due to an environment error. Consider using -- user or check permissions. We'll use -- user in this case. Cannot perform it. User-side packages are not visible in this virtual environment. All right, so that's kind of a strikeout. That's okay though. We're just going to skip the example and keep on going. The runtime of the k-means algorithm shows that it is an expensive operation, and to run 10 iterations takes 3.5 seconds. In the following example, the multiprocessing.pool.map, the method is used to distribute 10 k-means cluster operations to a pool of 10 processes. This example occurs by mapping the argument of 100,000 to the function do_kmeans. For multiprocessing, import pool. Okay, so here's some more code. You know what? We can try this code because it doesn't have any of the problematic modules. All right, let's give this code a shot. Oh, we do have, okay, so we do have that module. I'll give it another shot just to confirm. Oops, so same issue. Let's just keep on going. Oops, and there's some issue right now where I can't put down a bookmark. That's going to be a pretty big problem because without a bookmark, I'll lose my spot. Let's take a look at, maybe I can, okay, so yeah, it looks like I'm having a bug now where I can't place a bookmark. That's going to be a big problem for me. I'm going to need a bookmark or else I'm going to lose my place. So you know what? Right now I'm just going to highlight this so I know where my place is. And then I'm going to refresh. All right, and hopefully I can do bookmarks now. I can. Excellent. So now I can delete that highlight. All right, then let's keep on going. The runtime of each k-means operation is slower, but the overall speedup is double. This is a common issue with concurrency frameworks. There is an overhead to distribute parallel work. There isn't a free lunch to run the parallel code. The cost is that each task has a ramp-up time of about 1 second. This example shows why it is essential to profile code and also be careful about immediately jumping to concurrency. If the problem is small scale, then the overhead of the parallelization approach could slow the code down in addition to making it more complex to debug. From a DevOps perspective, the most straightforward and most maintainable approach should always be the top priority. In practice, this could mean that this style of multiprocessing parallelization is a reasonable approach, but not before a macro-ready level parallelization approach has first been tried. Some alternative macro approaches could be using containers, using FaaS, AWS Lambda, or some other serverless technology, or using a high-performance server that Python runs workers against, RabbitMQ or Redis. Function as a service and serverless. The modern AI era has created pressures that have enabled new paradigms. CPU clock speed increases have ground to a halt, and this has effectively ended Moore's law. At the same time, the explosion of data, the rise of cloud computing, and the availability of application-specific integrated circuits, ASICs, have picked up that slack. Now a function as a unit of work has become an essential concept. Serverless and FaaS can be used somewhat interchangeably, and they describe the ability to run a function as a unit of work on a cloud platform. High performance with Numba, with Python, high performance Python with Numba. Numba is a very cool library to experiment with for distributed problem solving. Using it is a lot like modifying your car with high performance aftermarket parts. It also leverages the trend of using ASICs to solve specific problems. Using Numba just-in-time compiler. Let's take a look at the officially documented example of Numba just-in-time compiler, JIT, tweak it a bit, and then break down what is happening. This example is a Python function that is decorated by the just-in-time compiler, JIT. The argument, no Python equals true, enforces that the code passes through the JIT, just-in-time compiler, and is optimized using the LLVM compiler. If this option isn't selected, it means that if something doesn't translate to LLVM, it stays as regular Python code. All right, so let's see if this works. I probably don't have those libraries, but we'll try it anyways. Oh, I have NumPy. And I have Numba already. All right, so let's give it a shot. So this is a decorator. We learned about these before. Unfortunately, I really didn't have a good understanding of decorators. I did a real Python tutorial of them, but I walked away from that tutorial kind of understanding decorators less than I had before. One kind of idea I have of decorators, and it could be a false idea, is that a decorator is basically just an argument passed to a function, but instead of actually passing a predefined function to the function, you can pass a function to another function as you're defining that function. You don't have to define it in advance if you are using a decorator. And I think that's a good working understanding of what a decorator is, but unfortunately I don't think it is the full understanding, and I think it's kind of a flawed understanding. Next, a NumPy array is created, and the IPython magic function is used to time it. Okay, so NumPy has no attribute arrange with 2 R's. It does have that attribute with 1 R. Oh, so rage is not defined. Let's go with range instead of rage. All right, let's give it another shot. You can do a page up to go through that faster. It looks like trace is not defined either. So yeah, and sure enough, that looks true. We don't see trace defined anywhere, so I'm really not sure what they're meaning to do with this. There's nothing that is trace. Now I do see this np.tnh, maybe that could be a typo and that could mean trace. But you know what, let's redefine it and let's not have trace there and see just what count is. The output shows that it took 855 nanoseconds to run the code. Okay, so we're getting output back without that trace. I'm not sure what the trace was for, but actually it looks like the code here took a lot less time. It only took 961 nanoseconds. The slowest run took 33 times longer than the fastest. This example could mean that an intermediate result is cached, 10 100,000 loops, best of 3, 855 nanoseconds per loop. The regular version can be run using this trick to avoid the decorator. All right, so let's try the trick. The output shows that without the JTT, regular Python code is 20 times slower. The slowest run took 4.5 times longer than the fastest. So here it looks like the code actually went much. Oh, I see. So this is in microseconds. So yeah, this took a lot slower. This is nanoseconds, which is a whole different unit of measurement. It's basically like saying feet versus inches. So inches would be the smaller unit. Likewise, nanoseconds is a smaller unit as well. So this code actually went a lot slower when we did the .py func than it did just with go fast there. With the Numba JIT, for loops are an optimization that can speed up. It also optimizes NumPy functions and NumPy data structure. The main takeaway here is that it might be worth looking at existing code that has been running for years and seeing if critical parts of a Python infrastructure could benefit from being compiled with the Numba JIT. And you know what? I have a using high-performance servers. Self-actualization is an essential concept in human development. The simplest definition of self-actualization is an individual reaching their real potential. To do this, they must also accept their human nature with all its flaws. One theory is that less than 1% of people have fully self-actualized. The same concept can be applied to Python, the language. Fully accepting the strengths and weaknesses of the language allows a developer to utilize it fully. Python is not a high-performance language. Python is not a language optimized for writing servers like other languages are. Go, Java, C, C++, C# or Erlang. Instead, Python is a language for applying high-level logic on top of high-performance code written in a high-performance language or platform. Python is widely popular because it fits into the natural thought process of the human mind. With sufficient experience using the language, you can think in Python just like you can think in your native language. Logic can be expressed in many ways. Language, symbolic notation, code, pictures, sound, and art. Computer science constructs such as memory management, type declaration, concurrency primitives, and object-oriented design can be abstracted away from pure logic. They are optional to the expression of an idea. The power of a language like Python is that it allows the user to work at the logic level, not the computer science level. What is the takeaway? Use the right tool for the job, and often this is the cloud or service in another language. So, yep, that's perhaps sometimes a disadvantage with Python is it's optimized for you, not for the computer. So there are some situations where you do want it to be optimized for the computer to get the most out of it, and you can do that with tools like the NumPy JIT compiler. Conclusion. Both DevOps and data science share a common thread in that they are both job titles and capabilities. Some of the benefits of DevOps methodologies are speed, automation, reliability, scale, and security accomplished through pragmatism. Using macro-level solutions for concurrency and management of processes increases operation efficiency. Using micro-level solutions before looking at available frameworks and solutions is a dangerous Python anti-pattern. Okay, so we're going to highlight that. What are the takeaways for Python in the cloud era? Learn to master the right concurrency technique for the task at hand. Learn to use high-performance computing library Numba to turbocharge your code with real threads, JIT, and the GPU. Learn to use FAAS to solve unique problems elegantly. Treat the cloud as an operating system and make it do the hard work of concurrency. Embrace cloud-native constructs such as continuous delivery, Docker format containers, and serverless. All right, so let's do the exercises. Now, I do remember IaaS, it's infrastructure as a service. And the benefits of that is instead of doing your own infrastructure, you can pay somebody else to do it for you. And then if you're a cookie baking company, you can cook your cookies, you can bake your cookies all day long, and you don't have to set up a server or manage IT or build your own website. You can just pay for somebody else to do that for you. Infrastructure as a service, IaaS, is a form of cloud computing that provides virtualized computing resources over the internet. IaaS is one of the three main categories of cloud computing services, alongside software as a service, SaaS, and platform as a service, PaaS, which brings us to the next question. What is platform as a service? So here I'm a little bit less clear on. I don't quite remember this, so let's look it up. Platform as a service, PaaS, is a type of cloud computing offering in which a service provider delivers a platform to clients, enabling them to develop, run, and manage business applications without the need to build and maintain the infrastructure such as software development processes typically require. What does elasticity mean? All right, so we're going to Google. So in terms of cloud computing, elasticity is defined as the degree to which a system is able to adapt to workload changes by provisioning and deprovisioning resources in an autonomic, that's a new word for me, manner, such that at each point in time, the available resources match the current demand as closely as possible. So automatic means involuntary or unconscious, relating to the autonomic nervous system, autonomic. So what this means is that when you require more processing, you'll get more processing. When you don't require as much processing, you won't get as much processing. So you can actually save money because you pay for what you need instead of paying for a device and getting whatever that device will provide you, you can just simply pay for the computing power and leave the device ownership up to someone else to maintain and manage and update. So if you need a lot of computing power and you didn't have an elastic system, you would have to pay for the maximum amount of computing power that you would ever need. So if, let's say you have a company that you want to persist for 15 years, and you know you're going to, on the 5th year, require a lot of computing, but then from then on, not require so much, you're going to have to build infrastructure that handles that really high amount of computing, and then just have it sit unused for the rest of the time. If you have an elastic system, though, you can just simply pay more for that one single year where you need more computing power, and then pay less when you need it less. So you can have elasticity if you use platform as a service or infrastructure as a service. That's something you actually don't get if you have your own equipment. What does availability mean? So this one, I believe I know the answer to. So computer availability is the mobile web application that provides real-time information on the availability of drop-in lab computers throughout the campus. So this doesn't look like a correct definition for that, but availability, as I understand it, which is probably good enough, is just the amount of time your system is functional. So there are going to be times, like, let's say there's a storm or like an earthquake or something where all of a sudden your system goes down. In order to have high availability, you need redundant systems so that it can just switch over. You're aiming for your system to always be up, but of course things happen, so you need to measure that availability and make sure it's as high as it possibly can be. All right, next question. What is block storage? All right, block storage, sometimes referred to as block level storage, is a technology that is used to store data files on storage area networks, or SANs, or cloud-based storage environments. Developers favor block storage for computing situations where they require fast, efficient, and reliable data transportation. All right, let's move on to the next one. What are the different types of cloud computing services? Okay, it looks like there's 3 types according to this. There are 3 main service models of cloud computing: infrastructure as a service, which we defined here, platform as a service here, and software as a service. What is serverless? Serverless computing is a method of providing back-end services on a as-used basis. Servers are still used, but a company that gets back-end services from a serverless vendor is charged based on usage, not a fixed amount of bandwidth or number of servers. All right, so what are some key differences between infrastructure as a service and platform as a service? The most distinct difference between IaaS and PaaS is that IaaS offers administrators more direct control over operating systems, but PaaS offers users greater flexibility and ease of operation. What is the CAP theorem? In theoretical computer science, the CAP theorem, also named Brewer's theorem after computer scientist Eric Brewer, states that it is impossible for a distributed data store to simultaneously provide more than two out of the following three guarantees. Consistency, every read receives the most right or an error, so that's the first thing that it's impossible to provide two or more out of. It's also impossible to provide availability if you try of these three things. Now you can provide availability, but you can only provide it with consistency or partition tolerance. You can't provide all three at once. But availability, every request receives a non-error response without the guarantee that it contains the most recent write. And the last thing that you cannot include, if you include the two other things, so you can have consistency and availability, but if you do that, you cannot have partition tolerance. The system continues to operate despite an arbitrary number of messages being dropped or delayed by the network between nodes. So that means that since you could only have two out of the three, and you've got three options, I think there's an equation for this. I think you can have, I forget what the equation is, but it's a combination equation. I forget what it is, but those kinds of equations are really useful to know. I wish I would. So of three options, you can only have two. So how many options do you have? I think it's 2 times 3. You have 6 options, but I could be wrong about that. But let's think about it. So we have options 1, 2, and 3, and you can only have two. You can only have 2 of those at a time. So you can have 1 and 2, 1 and 3, and 2 and 3. So I think I was wrong about that. There are only 3 possible options you can have. Still, you can have consistency and availability, where every read receives the most recent read, write, or an error, and every request receives a non-error response without the guarantee that it contains the most recent write. You can have consistency and partition tolerance, where every read receives the most recent write or error, and the system continues to operate despite an arbitrary number of messages being dropped or delayed by the network between nodes. Or you can have availability and partition tolerance, where every request receives a non-error response without the guarantee that it contains the most recent write, and the system continues to operate despite an arbitrary number of messages being dropped or delayed by the network between nodes. But you cannot have all 3 at once. You can't have consistency, availability, and tolerance altogether. All right, so next is Amdahl's law. In computer architecture, Amdahl's law, or Amdahl's argument, is a formula which gives the theoretical speedup and latency of the execution of a task at fixed workload that can be expected of a system whose resources are improved. And we, in this chapter, used Amdahl's law to study what happens when the resources of parallel processing are improved on a computer, and we saw that no matter how many cores you throw at it, and no matter how much of the cores you can operate in parallel, it'll always cap off at a certain amount of benefits, so that even if you keep adding cores, you won't get a improvement beyond a certain level. All right, case study questions. A company is hesitant to move into cloud computing because it has heard it can be more expensive. What are some ways to mitigate the costs of adopting cloud computing? So I would say the biggest way is to just make sure that you're monitoring your usage and you're not accidentally leaving your bills running. But here's three ways you can reduce cloud costs. You can avoid reliance on a single cloud provider. You can choose from a wider range of services and features to suit your applications. And the third way is you can make use of your existing on-premise infrastructure. That's a good point. That third way, if you already have some stuff going, keep using it and just purchase cloud only for what you need. You can save money by putting your equipment you already have to use and not just taking it out of commission. More ways you can reduce the cost of cloud computing are to stop unused and unresponsive instances, to create alerts to make sure that you're not leaving it on for too long if you don't need it, to utilize your cloud provider's auto scaling, to monitor to reduce cloud traffic, buy reserved and spot instances, serverless computing, don't migrate every app, use AI and machine learning. What is an example of a cloud-native architecture? Draw an architectural diagram for a cloud-native system and list the key features. So I'm not going to do that. Instead, I'm going to just Google it. So we've already got some diagrams here. We're just going to look over these diagrams. So here's a cloud architecture. So we've got our users here accessing a graphical user interface, and then we've got an orchestration service here where they can purchase storage. They can purchase networking, all sorts of stuff. So I think I'm gonna leave it at that. I just think the work I put into that is just not going to pay off. So I'm gonna skip that, go to the next one. What do spot or preemptible instances do? How can they save money? What problems are they suitable for? What problems are they not suitable for? So we're going to learn about preemptible instances. So a preemptible VM is an instance that you can create and run at a much lower price than normal instances. However, Compute Engine might stop, preempt these instances if it requires access to those resources for other tasks. Preemptible instances are excess Compute Engine capacity, so their availability varies with usage. Okay, so they do have some limitations. Compute Engine might stop preemptible instances at any time due to system events. The probability that Compute Engine will stop a preemptible instance for a system event is generally low, but might vary from day to day and from zone to zone depending on current conditions. Compute Engine only stops preemptible instances after they run for 24 hours. Certain actions reset this 24-hour counter. Preemptible instances are finite Compute Engine resources, so they might not always be available. Preemptible instances can't live migrate to a regular VM instance or be set to automatically restart when there is a maintenance event. Due to the above limitations, preemptible instances are not covered by any service level agreement. The Google Cloud free tier credits for Compute Engine do not apply to preemptible instances. All right, so that's it for chapter 9. Really excited that I decided to make another video on this today because I got through chapter 9. So make sure my bookmarks are all in order. I don't have an extra one. Okay, so I don't have an extra one. Yeah, chapter 9 was, I think, a lot better near the end. I really like these stories that they tell. It really kind of gives me a better, give me a good understanding of what they're dealing with cloud computing. Just understanding at a surface level is something I really didn't have a good grasp of. So this book is definitely helping me with that. So yeah, I was perhaps a bit too hard on it, so I'm going to try to keep going with this book. I did start another series, so I'll be working on multiple series concurrently, just kind of doing whatever I feel like doing that day. So thanks for watching, and I'll see you in the next video.